This lesson is about wave interference and the double slit experiment. So we've talked about waves, and this is going to we're going to focus on light. Light is an electromagnetic wave, and over time people have been very um, interested in the properties of light. People like Isaac Newton, Thomas Young, other scientists have found that the nature of light is somewhat elusive because sometimes light behaves like a wave, and sometimes it acts like it's made of particles, and sometimes it acts like both. So we have three leading theories that we use to explain light, and three models. Which model you use depends on how you're looking at light. So today we're going to look at one of them, and other times we'll look at other models depending on what we're trying to explain. So the first model that we'll use today is when we do wave optics. This is the wave model. This says that light acts like a wave, and it can interfere with other light waves. We'll also see that we can use the ray model. So generally people think of light as moving in a straight line, just like a ray of light. This model is used for when we look at mirrors and lenses and refraction of light. This is ray optics. The final model is the photon model. This says that light behaves neither as a wave nor a particle. It's made of photons and it has properties of both. So let's look at wave optics. So light acting as a wave. If we consider light as a wave, we find that the light waves can reflect off of surfaces, they can diffract, and they can interfere with each other. We're going to talk about some details of that. So first, wave interference. And we talk about superposition. That means that when two or more waves happen to be simultaneously present at a single point in space, they can interfere with each other. The displacement of the medium at that point is the sum of the displacements due to each individual wave. And you can see this most obviously in the ocean when you look at two waves coming at each other and what happens. And so if I had a string, this might also model it. I have one wave coming to the left and one wave coming to the right. When they overlap each other, you can see that the amplitude of the wave is greater. They get larger because they combine. Then they continue moving, and this one that was on the right is now moving to the left, and the one that was on the left is now moving to the right. So when they are exactly at the same point, their waves interact with each other. This example is called constructive interference. This is when the crests and the troughs are aligned in waves that interfere with each other. So an example, before interference coming from the left and coming from the right, during interference they create this green wave, and then they continue to move on their own way. We can also have, so this is an example where the interference leads to a larger amplitude wave. We could also have destructive interference. Destructive is when the crests are aligned with the troughs and the waves interfere by basically for a moment negating each other. We have one that's a crest coming and meeting a trough, and when they interfere, they create this green line, which is just a flat surface. There's no wave there. So here's another example of destructive interference. We have one wave coming at 1 meter a second, another wave coming. They get near each other, they meet, and then they combine. And for that time, we have no waves present. Then they continue moving in the opposite directions, and both waves emerge unchanged. So we're also going to talk about diffraction. So another type of interference we could have is a wave is going to pass through a barrier. A barrier causes it to spread out. So an example of a very large barrier, let's say we have waves coming in this barrier, and they're just going to continue to move straight forward because the barrier is very large. If I make a smaller barrier, one that's a barrier that's small compared to the wavelength of the light, when the wave comes through it, it spreads out past the opening. So this is diffraction of light. The section where it's not diffracted is called the shadow section. But oftentimes we do have a slight interference or slight diffraction in the shadow. You can see a little bit of diffraction here and even a little bit on the edges here. Now that diffraction around the corner diffraction around a barrier. This is what allows you to hear sounds when you are around the corner from someone, but you can't see them. The sound travels as a wave, and it will diffract around an opening. So diffraction of sound waves allows you to hear sound when you're around the corner from the source of the sound. So if I have diffraction, let's look at diffraction of light, and we're going to have a laser, and it's going to hit a space that has a very, very small slit, and rather than traveling just in a straight, narrow path, the light will spread out behind the slit. So this diffraction will allow the light to travel in many directions, or in a wider area once it goes through the slit. Now, this is a single slit. What's the more interesting case that we're going to talk about now is what Thomas Young did, which was a double slit. So he has light from a laser coming through and hitting two very small slits compared to the wavelength of the light. And then the light travels through and it diffracts on the other side. But now I have diffraction of one set of light, light from one slit, and diffraction of light from a second slit. And those waves, those light waves, will interfere with each other. And so what ends up happening is we get this interesting projection on a viewing screen as the light travels through the slit. So the distance between here and here is actually much, much larger than the distance between the slits. We're just showing it for an example. So let's talk about what's going on in terms of interference here. So if I have light I have one light wave, or one light projection coming through the slit, and it's interfering with another, you're going to notice different kinds of interference happening. So first we have constructive interference. The light coming through this slit is going to be have constructive interference with the light coming through this slit, which means it will have a larger magnitude. So it will make a bright fringe on the viewing screen when the two amplitudes are added together. So this is an example of where we would have constructive interference. This is when the two lights are combining together and making a larger amplitude. We have many bright fringes. Each of these is constructive interference. Every bright fringe is constructive interference. We also have points where the light is, the amplitudes of the two waves are subtracting from one another, and that makes no wave coming through. It makes a dark fringe. This is destructive interference. So all the dark fringes are examples of destructive interference from the two sources of light. So Young's double slit experiment, here it is from overhead. We have light coming in of wavelength lambda. It's coming through these two slits, and then we have our constructive interference and our destructive interference. And we have two equations that are on the physics equation sheet that tell us how we can find out more information about the double slit. They describe the properties of the double slit experiment. So this is the first equation and this is the second equation. So delta L equals m lambda. M is an integer. It starts with 0. Right in the center of the two slits, we have what's always the brightest fringe, and it's called the central maximum. And we call m as just a letter we use to identify what number fringe it is. So this is the 0 fringe. This is the first fringe. This is the second fringe, the third, and the fourth. And if you go in the other direction, we also have the first, second, third, and fourth. So m is just the order number of the fringe. The order number of the fringe times the wavelength of the light will tell us the difference in the length of light, the path length. So in this picture, they're labeled by R, R1 and R2. But in the equation, it's using L. It's just the length from the slit to the fringe. This length R2 and this length R1. So R2 minus R1 is our delta L. Delta L is L2 minus L1, or R2 minus R1. That tells us the path length, the difference in path length. The difference in path length is equal to the number of the fringe times lambda. So as you increase your number of fringe, you're going to have a larger difference in path length. So as you go further away, you'll have a larger difference between these 2 points. All right, The other thing we can look at is the angle, and let me do another picture for that. Let's say we are going through the double slit and we have an angle. This is the angle with the zero. So with the central maximum, this is going to be our zero line right here. The angle of R2 and the angle, we can find properties of the double slit projection using this angle. So if I take D is the space between the slits, it's actually a very, very small number, times the sine of this angle, it will give me the number of the fringe times the wavelength of the light. So D is the distance between the slits, sine of theta is the sine of the angle, m is the number of the fringe, and lambda is the wavelength of the light. Now notice, this angle, when we do double slit problems, is going to be in radians. You need to set your calculator to radians, not degrees. So let's look at these equations and see kind of what information we could get from it. Let's say we have a light of wavelength lambda 1. It's going through a double slit, and the interference patterns are observed on a screen. When the wavelength is changed to lambda 2, the fringes get closer together. So is lambda 2 going to be larger or smaller than lambda 1? So we want to look at what makes the fringes closer together. The fringes closer together is going to be the difference in the distances. So if the difference in the distances is getting smaller, what is happening to lambda? Lambda must be getting smaller. Lambda 2 is smaller than lambda 1 because the distance between the fringes is closer together. So we talked about double slit. We also could look at single slit. It's not as often that we look at it. We don't have equations for it. I just want to show you what it would look like. If I shine light through a single slit, it's not going to have the same kind of interference. Your projection on your screen is going to look like this. And you'll notice that the fringes have different widths, and it's very, very bright in the center, and then it gets less and less and less as you go away. So let's compare a single slit and a double slit. If you could see the light, the total amplitude of the light hitting the screens, it's going to look a little bit different. Now it does decrease, both of them decrease as you get further and further away. However, the difference between this slit and this slit is not very much compared to the difference in this slit and this slit and this slit and this one. We also notice that the width of the fringes is the same for a double slit experiment, and the width of the fringes for the single slit experiment is not the same. The bright fringes are going to be equally spaced here, but not here. And the other variation of this that we can do is called a diffraction grating. So instead of having a single slit or a double slit, we're going to have a whole bunch of slits. And we'll say n closely spaced slits. It might be 5, it might be 100. All of these closely spaced slits create what's called a diffraction grating. So we're still diffracting the light the same as we did with single slit and double slit, but now we have a lot of slits, and we can use this to see some interesting properties of light. If you have a diffraction grating, your projection is going to look something like this. You'll notice that the distance between the slits is not exactly equal. And the brightness it's much thinner projection. We're not going to do equations with this, but I want to talk about what this is useful for. We use diffraction gratings for looking at the properties of elements, which comes from the light that comes off of those elements. So in spectroscopy, we're going to use diffraction of light in spectroscopy. So we have a diffraction grating here. And if we're going to take properties of certain elements, atomic elements, if we excite them with light, electricity, or collisions with other atoms, each element will emit light that's characteristic of what they're made of. So this is especially useful for astronomers who can't go out and actually touch what's in way in outer space, but they can look at what kind of light comes from the objects in outer space. So by analyzing the properties of an object's light, astronomers can infer the physical properties of the object. So if we have an object and the light goes through diffraction grating, the diffraction grating will break it up by different wavelengths, and you'll be able to see if you looked at the center, all the light is going to overlap, but individual components will be broken up, and so you can look at the projection on the screen and you can see what types of wavelengths are coming from that object, and that types of wavelengths will tell us what the properties are. So here we would see blue light and violet light, and that tells us that the object that it's coming from is emitting blue and violet light, which we can use to learn more about the element.